How does the violent alternating current surging out of your wall outlet get forced into the steady, single-direction flow required to charge your phone battery? Electricity naturally flows toward the path of least resistance, regardless of direction. Left to its own devices, it will simply surge back and forth, unless a specific component forces it to do otherwise. This diagram shows the diode, the foundational building block of modern electronics that solves this directional problem. Notice the physical configurations here, specifically the labeled anode and cathode terminals. At a macro level, the diode is the electrical equivalent of a one-way plumbing valve. It permits flow in one direction and completely blocks it in the reverse. Swap the water for electrical current, and the result is exactly the same. Yet a diode achieves this one-way flow without a single moving physical part.
To understand how, we have to look past the copper and dive directly into the quantum architecture of semiconductors. A standard diode is created by fusing two differently doped regions of silicon together. On the left is the p-type region. Its majority charge carriers are positively charged holes, which are essentially empty spaces roaming through the atomic lattice. On the right is the n-type region. Here, the majority carriers are free, negatively charged electrons. At the exact moment these two materials make physical contact, high-energy free electrons from the n side immediately begin to diffuse across the border. This illustration shows what happens next. These crossing electrons fall into the empty holes on the p side, a process called recombination. This combination strips the involved atoms of their electrical neutrality. They are locked into place as static charged ions. This creates a gray void known as the depletion region. It is an area completely wiped clean of any mobile charge carriers. The exposed static ions left behind create a permanent, localized electric field. This field physically repels any further electrons from crossing the junction. This self-sustaining electric field establishes what we call a barrier potential. It permanently breaks the electrical symmetry of the silicon, creating our one-way valve. To manipulate this internal barrier, we apply an external voltage, like a battery. Connecting the positive terminal of the battery to the anode, the P region, and the negative terminal to the cathode, the N region, creates a condition called forward bias. This specific polarity actively pushes the majority carriers on both sides toward the center junction. If the external voltage overcomes the intrinsic 0.7 volt barrier potential of the silicon, the barrier collapses, current flows freely. Reverse bias occurs when we flip those battery connections. Reversing the polarity violently pulls the charge carriers away from the center junction. The depletion region tears vastly wider. The main current drops to zero. A microscopic leakage current persists, but this is only due to ambient thermal energy generating rogue carriers. The diode's ability to act as a switch is governed entirely by whether external voltage shrinks or stretches this atomic dead zone. These microscopic atomic movements map directly onto a macroscopic engineering tool. This graph illustrates the voltage-current characteristic curve. Voltage is plotted on the x-axis and current is plotted on the y-axis. Under forward bias, looking to the right of the origin, the current remains functionally at zero until the voltage approaches that 0.7 volt mark. As the voltage crosses 0.7 volts and the barrier collapses, the current rockets upward exponentially. Under reverse bias, negative voltage results in a flat, near-zero line, representing only that tiny thermal leakage current. If extreme reverse voltage is applied, valence electrons are violently torn from their covalent bonds, initiating an avalanche breakdown. Unless a diode is specifically designed for this level of stress, pushing it into the breakdown region will permanently destroy it. This highly nonlinear graph is not arbitrary. It is the exact mathematical signature of the quantum energy hill we just explored. The true exponential physics of the diode curve is mathematically cumbersome for rapid, everyday circuit design. This chart shows how engineers use tiered approximations. We start with the ideal model's perfect 90-degree characteristic curve. It treats the diode as a flawless switch, used for high-level troubleshooting to determine if a path is open or closed. This diagram shows the practical model, acknowledging the physical barrier by adding a 0.7 volt opposing battery symbol into the equivalent circuit. Notice the vertical current line is physically shifted right by 0.7 volts. This model is used for standard low-voltage design. Finally, this visual shows the complete model. It adds a small resistor to the circuit, known as forward dynamic resistance.
Here, the upward line is slightly sloped to account for voltage increases as current rises. This is reserved for high-precision design. Effective engineering is the art of choosing a mathematical model that sacrifices just enough quantum reality to achieve maximum practical utility. We can now apply these models to solve the problem we started with, taming the alternating current from a wall outlet. This half-wave rectifier circuit feeds raw AC into a single diode. During the positive half cycle, the forward bias diode allows current to flow. When the cycle reverses, the reverse bias diode entirely blocks current. The output leaves only a pulsed, direct current. This exact physical process is what happens inside a phone charger. Additional components simply smooth out these pulses to make the power usable for your battery. By organizing microscopic impurities in a small block of silicon, we can unilaterally dictate the flow of massive electrical systems. The most profound engineering tools require no moving parts at all.